Welcome, this is your stats friend, and we are going to quickly and expertly crush simple slopes analysis. Maybe you're here because you're doing a dissertation and you need this analysis. You've been asked to do it. Maybe someone at work asked you to do it, or maybe you just want to get really good at statistics. In any case, you've come to the right place. Please note I have online classes and I offer consulting. See the links in the description. I have a class for linear regression that includes simple slopes. So what is this simple slopes thing? Basically what it is the idea that when we know we have an interaction, we then want to know, do the slopes differ under two different conditions? If you look at the top right here, I have an example, and this is the exact example we'll be working through today. What you'll see here is we want to understand, is this relationship between education and happiness, or the slope of those lines, the same or different among those who watch a small amount of TV every day and those who watch a high amount or large amount of TV every day? Looking at these, you can see that there's a larger slope for the red line, obviously. However, is that slope significantly different from the blue line? In most cases, you can't tell just by looking. It will depend on a number of factors, including sample size and other things. What we really want to know, should we think of this relationship as different among those who watch a little or a lot of TV? So we'll show you how to run this analysis, make visuals like this, and then to test the significance between those two slopes. That's why we're here. When you have an interaction, you may refer to one of your predictor variables as a moderator. This is an arbitrary decision that you've made. Our software program doesn't care about this distinction, but we can think of one in that way. In the example here, we could say that the effect of education on happiness depends upon how much TV you're watching, or is moderated by TV viewing behavior. In that way of explaining it, we are treating TV viewing as the moderator and education as the predictor of happiness. However, we could say the reverse just as easily. We could say that how TV viewing affects your happiness depends upon education. And we could graph this in the reverse. Usually you'll want your moderator to be separate lines and your predictor to be determining the slope, as the predictor and the outcome variable are what the slope is based on. You may even want to run simple slopes once in both directions, treating each one as the moderator once and repeating the analysis. I'm going to show you two ways to do this. There are timestamps below so that you can skip ahead to the ones that you want. You can also skip the first section if you'd like, which is on prepping your data. We're first going to do the SPSS method, which is simple, just uses SPSS. You don't need anything else. And the second uses Hayes process, which is a free additional module for SPSS. So choose which one of those you'd like to do. If you're here for education, you may want to view both. But if you simply want to move through a project and get to the right answer as quickly as possible, choose one. Choose standard SPSS if you have no idea what Hayes process is. If you already have process or you've been asked to use it, then probably that's the better one. It is a little more powerful, but not necessary. So the most important thing to consider as you start this is something that is horribly overlooked in many cases, and that is to ask yourself before beginning which of these two approaches is correct. And again, this may involve asking whoever it is you're working with or for on this project. One is a statistical way where we simply find the average for both of our variables in the interaction, then create versions of them at +1 and -1 standard deviation to represent high and low scores on those scales. So in this case, that would give us something like those who are 1 standard deviation below average of our sample for education, and those that are 1 standard deviation above, as well as compared to all others in this sample, those who are watching TV a standard deviation less or a standard deviation more than average. It is useful. However, what does this mean to someone looking at the end result about how much education they would need or how much TV they should watch to obtain a certain level of happiness? To most people who don't do statistics every day, it means very little. They understand less and more, but it's much more real if those values can be interpreted in a way they understand. So the second version, which is almost always preferable unless there is no way in which you can create meaningful points, will not only be more sensible to those who read it, but may actually be more valid in many cases. Take, for example, if this was, instead of a study on happiness, one on depression. What if we used scientifically validated cutoff scores for depression as a diagnosis? That would be really interesting compared to just random scores in the population. In this example that we have of TV and education predicting happiness, we could pick something like to say 1 hour of TV compared to 4 hours per day. Perhaps someone's working on a campaign to convince people to limit their TV time to 1 hour per day. So they want to highlight that specific condition compared to a more typical 4 hours per day. And we could also use 12 versus 16 years of education, because 12 years means you've completed high school. 16 years means that you've completed college. So this would make more sense. Ultimately, we would say, how does getting a college education impact your happiness compared to a high school education? Or how does cutting your TV from 4 to 1 hour per day, or increasing it from 1 to 4 hours per day, impact your happiness? That makes a lot more sense. Also, you can mix. You could take the standard deviation approach on one and a meaningful point approach on the other. Both are valid. Okay, let's get a data set opened up, clean it up, and show you how to do this analysis. If you have your own data set and you're only watching me do this with my data so that you know how to do it with your data, and you don't want to follow along with this example exactly, you can skip this section. The timestamps are right in the description so that you can do that. If you want to follow me through with this data, here we go. This is the welcome dialog. If you are not seeing this because maybe you disabled it because you were sick of seeing it, go to File, Welcome Dialog, and you'll be right here with me. By default, it will be showing your recent files on this tab. You want instead the one that says Sample Files. So I'm down here, Sample Files. Click on that. The one we're going to use here is near the bottom, and it's called surveysample.sav. Open that. Now this has a lot of variables we don't need. We're going to pare this down to just 3 variables, plus we'll keep our ID variable. This is a good practice for you anytime you pare things down to keep the ID so we can at least identify which participant it is. And that would allow us, if we wanted to go back to this massive data set and pull in anything that we decided we wanted later, rather than not knowing how to match it up with the person or whatever the ID means. In this case, however, we want only ID and then a couple other variables. We want the education variable, EDUC. We want the TV hours variable, TV hours. And then we also want happy, which is HAPPY. Okay, so all I'm going to do here is get rid of everything else by highlighting. I hold Shift here to highlight several at once and hitting delete. Okay, we don't need anything but these for our example. I'm using this because it's a really good data cleansing example, just because it's a lot like the data sets I've worked with that you download from government resources and things. It has funny codes in it, which we're going to look at now, and we're going to get rid of all the junk we don't need, and then make things the way that we want them. All right, so if you're with me so far, the first thing you may notice is that we have missing values listed here. When you see things like this, 99 and minus 99 or minus 999 or other things are very commonly used to say that the data is missing, but without leaving it truly blank. I'm not going to get into why people do this right now. I find it to be a little outdated in most cases, but we need to deal with it. So this means that those are data that we're not going to count. In this case, actually, SPSS is aware that they're missing and will skip over them for us. But I don't like to rely on that. I like to clean up my data sets. Again, this might be a bad practice in some examples, but here because we're looking at it, I don't want them interfering with what we see. So let's look at the education variable first of all. I double-clicked that on the left to automatically go to this view. Let's first sort ascending and see that some people have 0 education, but that is probably valid. We'll check to make sure. And then let's sort descending. And here you can see they're using those missing data items here. 99 and 98 are not valid. Maybe someone making a joke about lifelong education, but in this case, we know that those are not valid. So I'm just going to delete them. Now for happiness, the only valid scores are 1, 2, and 3. By the way, that means that using linear regression on this may not be an ideal approach. It's a bit chunky having only 3 options. But we're not here to deal with that today. So if you notice that and you're aware of that due to having some skill in statistics yourself, let's just let that slide. It's still a reasonable scale to use here, and it will serve the purposes of our example. Let's again sort ascending. 1 is in fact the lowest for this scale, so those are all valid. When we sort the other way though, we see that we have lots of 9s and 8s. So let's delete all of those because 3 is the highest score available. TV hours ascending. No one's watching a negative amount of TV. But we all have that one friend who wants so badly to let you know that they don't watch TV because they're too smart or intellectual for that. Maybe that's what -1 is. I'm kidding. Delete them. But TV hours 0 is valid. That just means they don't watch any. All these crazy numbers like 99 are also not valid, including 98. 21 seems a bit ridiculous. That would mean you sleep for 3 hours and spend the rest of your day watching TV. So in a real study, we might want to worry about that and maybe delete it as invalid. But in this case, we're going to leave it because it looks like someone answered that way, and I guess maybe that's the life they're living. Let's double click any of these labels now to go back and look to make sure what we did makes sense. Here are the missing labels I used to make those determinations, how I knew 98, 99, and -1 were not valid. Again, you can leave them in, but I think it's nice sometimes just to clean it up and look at it. We don't need to include those for this. Let's also look at the labels. So that we know what we're really dealing with here. So highest year of school completed. So that means 12 would be high school, for example. General happiness, so it's about life in general, I guess. And hours per day watching TV. Right when I first looked at this, I didn't know if TV hours was weeks or months or days worth. It's per day. Now under our values, there's something interesting. I already know from looking at this before, so I'm going to draw your attention to it. Click on the 3 dots for happy and values. This is labeled 1 very happy, 2 pretty happy, and 3 not too happy. Oh man, that's reverse in my mind. I don't like that at all. First of all, I'm going to get rid of these other labels that I don't need, because it might try to pull those into graphs and things later and just murk the waters. We don't need that. And then I want these to be reversed. I do not like 3 being lower happiness than 1. So I'll show you how to fix that. We will change this label, but I always like to first change variables, then the labels, just so I know in my mind the order I do things, so I don't do half of the job and switch the labels without switching the data or something like that and have incorrect data. Let's go to transform, recode into same variables. This will actually overwrite the data in that variable, so it might not be the best to use in all situations, but we're just doing a tutorial here. Put general happiness into here, click old and new values. We want 3 to become 1 for the lowest score, 1 to become 3 for the highest score, and 2 we actually don't want to change, so what I'm doing right now isn't necessary, but I like to see it to know that it's going to be kept the same. Now that that's done, it's the way I want it, but the variables are now labeled incorrectly. I didn't mean to delete that, but we'll put it back. I now want 3 to be very happy. Two can remain pretty happy. And 1 will make it what it was before, which is not too happy. Strange wording, but that's what it was. So now we have a little bit more of a sensible scale there. Now, a higher number is in fact more happiness. We can verify that by coming here and clicking this button, which will swap between the number and the label. Looking good. So from here, we're now ready to begin a little bit of testing. We've cleaned this up a bit. We have our education and TV, which we want to use to predict happy. So let's go and run our first regression. Go to Analyze, Regression, Linear. Very likely you've already done all of this with your data, and I'm just now going to arrive where you are, test an interaction, and see that we have an interaction. Before we test the interaction, we'll just run a good old-fashioned linear regression. We want to predict happiness from education and TV. Let's also turn our descriptive statistics on, just so we can see them, and collinearity diagnostics. Those will be nice to have later, so let's just turn them on and leave them on. Click OK. We get a general result telling us that both of our predictors, education and TV watching, predict happiness. We can look here to see the direction of that effect. A positive number here means it's positively associated. So education is in fact related to being happier. And watching TV, since it's negative, is related to being less happy as you watch more TV. Now we need to run an interaction. Interactions are just multiplying your two predictor variables together, unless you have a categorical predictor. That's covered in my online class, or if you reach out to me, I can help you with that. Here we're just covering the most basic interaction that you'll probably face, which is a continuous versus continuous interaction. So we need to create a variable. Go to Transform, Compute Variable. And we're going to create our interaction of TV and education. I like to use that X to represent the interaction or the multiplication of the two. You can call it anything you'd like. So we put TV in here, multiply that times the education variable, and now we have here what we're saying we have here. Great. Some of these didn't have a valid value for TV, but let's look at the rest and see if it's doing what it's supposed to do. 14 times 21 is 294. Yeah, these look right. So we're good to go. Let's go back to our regression, which you can do through the menu system, or more quickly with this button to go back to things you've done recently. Let's add our interaction term. You could also add it as a second block to check for the significance of the interaction and things. Here we're just going to run it in the simplest method. And now we see that we have a significant interaction effect. You probably already arrived at this point in your research to even know that you needed simple slopes. Once we have this, now it makes a lot of sense to do a simple slopes analysis, because we want to see that effect in more detail. What it means when we have a TV and education interaction means that the effect of TV depends on education, and the effect of education depends on TV. That is, when we have high levels of both, or a high level of one mixed with the low level of the other, we get an additional effect beyond just the main effect of knowing each one of these alone. They interact, rather than being completely independent of each other. Next, we really should take a look at our variables just to see what we're working with here, as well as then create several new variables so that we can do the additional testing that we need. All the new variables will be versions of the ones we have or combinations of them in new interactions. But we need to create several. So let's first do descriptive statistics on what we have and go from there. If you go to Analyze, Descriptive Statistics, Descriptives, we can enter our three primary variables here and go ahead and click Save Standardized Values as Variables. That will create a standardized version of this. When you decide to do this, you may use your raw scores just as they are. You may center your variables, which is to make the mean of each 0 by subtracting the mean from every score. Or you may standardize your variables, which is what we're going to do here by creating Save Standardized Values. That's when you get the z-score for each score, which means how many standard deviations is it from the mean. There are several options in there on how to do that. This is the quickest way to create your z-scores. If you wanted to create centered scores, it would be done a little bit differently. Here we get just some basic information about our data. I would recommend you save this somewhere, such as Excel, so that we can refer to it later. What we can see here is that our average education is 13.25 years, which is high school plus 1.25 years. So I guess on average, about 1 year of college. Our general happiness is 2.2, which on a 3-point scale seems pretty happy. Right in the middle of the scale would have been 1.5. However, this was really just an ordinal scale, and that middle one was pretty happy. So that's not a bad choice. And on average, the people in our study are watching 2.86 hours of television per day. We can also see for each of these the standard deviation. And our sample size here of how many gave us a valid score in each instance. So you can see we have 2,000 and something people in this study. We also have, as we discussed, new variables now, which are the z-scores for our main variables. We're not going to use the one for happy, but we went ahead and created it anyways, just because it was part of the procedure. In fact, I'm going to delete it just so it doesn't clutter up what we're doing. However, we do want our standardized education and TV hours variables. If instead you wanted to make those centered but not standardized, you would instead have done something like this. Go to Compute Variable, add whatever variable it is that you want to change, like education, and subtract from it the average education of the group, which was 13.25. Right over here, this is why I saved that, so we could refer back to it. And then this would be, I would call it something like that for centered education. You do the same thing again for your other variable. 2.86 was our average for TV viewing. Let's call it CTV for centered TV. Now, if I showed you all the ways to do everything, this video would take entirely too long. So from here on out, I'm actually going to not use the centered ones at all, but I wanted you to see how to create those. I'm going to use mainly the Z versions, which are standardized, and also the original version a little bit, because then we can show that version we talked about at the very beginning of using specific cutoffs that actually mean something. Or I shouldn't say cutoffs, but set points for amount of education or number of hours of TV. So at this point, if you know you want to do the +1, -1 standard deviation approach, you could move forward really just using the z-score versions. If you know you're picking certain points, you would move forward using just your raw scores, and you didn't need to create the z-scores for the purpose of your graphing at least. However, it's good to create the z-score version in either case because it is a little bit better for looking at some of the statistics. We'll see that as we go through here. So the first thing that we're missing is that we need an interaction term based on the z-score versions that we just created. So let's make those first and foremost, or make that first and foremost. We're going to want to take our new z-score versions of these two variables and multiply them together. The order there doesn't matter. And I like to give it the same name as before, but with a z in front of it. If you were also going to make one from the centered scores, which I'm not, maybe add a c. But we know that that's the interaction of the z-scores. Now let's look at just the regression results to understand them a little further. I'm going to run this one again. It's the same one I ran just a moment ago. This is with our original version of the variables and the interaction in the model. And we see that we have some problems with multicollinearity. Anytime you have a VIF above 5, you're in the problematic range. Above 10 is pretty severe. So a lot of people would hesitate to report these as they are. Now, when we interpret the interaction, we do not have any concern about these VIF scores really, because we always get them with an interaction term. And of course, they're highly related. What multicollinearity means briefly, since we're not going to go into it in this video, is just that these three variables, particularly the ones with high scores, are too similar to the other ones, too highly related. Or that their relationship to the dependent variable is too similar. So we need to do something about it if we want to report these as good results that we can say don't have any bias in them. But again, the actual last result here, the interaction term, is 0.002. We are not concerned about that high VIF because the interaction term is always redundant to the existing terms because it includes them. They're multiplied together. So usually they're very similar and we get this sort of problem. But that's okay. What we want to see here is really the numbers that we get, which we could still use to construct graphs and things like that. However, we can rerun the model just by standardizing all of the terms. It will take care of that multicollinearity problem in this case and in most cases. So if we put in the z-score versions, and run it again, we'll see that the significance of our interaction is exactly the same. And I knew that it would be. But now our VIFs are all very reasonable. So what's important here is we can notice that actually the significance of the main effects, which is the two variables before they're into the interaction, these are now highly significant, whereas before, the second one, TV, was not. Which of these would we trust in this case? The answer is the second one, because we've taken care of that multicollinearity problem. Now we can't interpret from these too much detail about the main effects because anytime there's an interaction in the model, it makes the interpretation of the main effects a little bit murky. But what we can do is say that this is the better of the two for determining the significance overall. And we can report it now without the multicollinearity problem, which some people would claim changed our result. It doesn't really, but it does help us identify the actual significance here. So from this point, what we want to do now is to actually do our simple slopes test. We know there's an interaction. It holds true whether they're standardized or not. And it looks like our main effects still matter as well. But now we want to know, at high levels of one of the variables held to those higher levels, then what's the relationship? And when one of those variables held to lower values, what's the relationship between the other predictor and the outcome? So let me show you how to do this. The first thing we need to do is create new variables. we need a high and low version for any that we want to test this way. You may only need it for one of yours, but you'll probably want to do it for both. Go to Compute Variable, and we're simply going to take the existing variable and add or subtract one standard deviation to create our high and low versions. So let's start with the z-score versions. If we have education converted to a z-score, which means it has a mean of 0 and standard deviation of 1, to add a standard deviation, we just add 1. It seems overly simplistic, but it's only that way because we already standardized it. So here, I'm going to name it Z High Education, because that tells us all the information we need to know about it. And I've added 1. When I subtract 1, that makes it our low version. You might notice it's sort of simulating the low version. It's not taking the scores we have that are low, but moving them all lower. The impact that this has is seen only really in the interaction effect, in that the slope of the main effects, if we had no interaction effect in the model, wouldn't change just because we move all the numbers up and down a little. But the interaction does because those are multiplied together. So larger numbers become even larger when multiplied together. So it is sort of simulating what would it be like if we had lower scores or higher scores. It also tells us then how is it predictive at the higher and lower ends of the scale. So let's click this low one here. And you'd keep going creating any that you need here, okay? So I would say we also want to do this for TV. So ZTV hours. And again, add 1 and then just subtract 1 to get the two things that you need. The high version of TV. Simply switch this to a minus. And we'll get the low version of TV. Now, when you're doing this in your ordinary variables that are not standardized, it's actually sort of a little more difficult. Just that we're not going to add and subtract 1, but actually the correct standard deviation. Or, in this case, remember we said we wanted to simulate a particular set. We said we wanted to know 1 hour of TV versus 4, and 12 years of education versus 16. So in that case, we need to look at what we've saved here, where we have our means and standard deviations, and use those to realize what we need to do. So let's say I want to make first high TV. The Z went away because I'm going to make it from the regular TV score. But now, let's say I want to make the high one first, as I put here. What do I add to that if I decided my high number was going to be 4? Well, let's see here. Our hours per day of watching TV on average is 2.86. We want to move that up to 4. So we need to make up that difference, which happens to be 4 minus 2.86. You can use a calculator to make sure that you get this right. I recommend it. I make mental math errors more often than I make other sorts of errors. You know, I think I'm too smart for the calculator. Maybe I'm not. So that gives us 1.14. And that will give us our high TV because it's going to move the mean from 2.86 up to 4, which is what we said we wanted. But I'm going to change something here because actually this is more specific. You could just call it high and know what it means, but I'm going to put 4 hours TV because that's actually what it is. And I like that label better. Oh, I forgot though. Can't start with a number. I always forget that, even though I've been doing this a long time. So now we'll say hours for TV, and it'll like it better. Now, what about our low? We decided we wanted 1. Well, 2.86 to get to 1, we want to subtract 1.86. And that will be as if everyone had on average 1 hour of TV watching. What about for our education variable? Well, let's get that in here. And let's start with the higher version. We said we wanted 16 to be our higher number of education years. So to follow the same form, I'm going to say years 16 education. What do I need to do to go from 13.25 to 16? Well, use your calculator again. Again, I know it's not that difficult, but you'd be surprised how often you'll just make a little mental error and not realize it. We need to add 2.75. And then we wanted 12 years of education as our other level. So what do we need to do? That's going to be, now I know I'm breaking my own rule here and not using the calculator in one direction, but it is a little bit easier even to see this in this direction, right? So it should be 1.25 that we need to subtract. Now we're not quite done making variables. We still need interactions for the new things that we've created. This time I'll show you just how to create one of the interactions, and then I'll skip ahead to where I have them all complete, and you can pause and catch up as needed. To make these interactions, we want to give them a name that keeps in mind all the things that we've created. And we'll need one for each combination, which is to say, when one is high and the other is low, or when both are high, when both are low. We'll need all of those interactions to be able to test all of the different things that we could test. So let's just think of one of them and start with our non-standardized original variables. And let's say we're going to focus on TV and say when we have a lot of TV watching. So let's say when they're watching 4 hours of TV, that little asterisk in there for multiply. And then we have to ask ourselves, what do we want it by in the other one? Well, there are several of them we'd like to make. The most basic one, if we wanted to see if the levels of TV relate to then the relationship between education and happiness, then we would want to use this high level of TV with the ordinary education variable. But you can see there are a lot we would create here possibly. We might want, when it comes to education and TV, or TV and education, we might want high, 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 low, 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 high, and also those original versions. So let's call those normal, high normal, low normal, normal high, normal low. There's several you could make, and those are all interesting. You throw into the model to see what you get. So the last thing I'll say before cutting away to make all these on my own and come back, and to let you do the same, is to make sure your naming conventions include everything you need. So before, we were using an X to indicate our interaction, so we want to do that again, but let's say, like in this case, something like for TV and education. Now when I change that, in the cases where I use the 16 or 12 for education in years, I would also put that in here so it's fully descriptive and we know which one to add. So for all of those that you might need, go ahead and run those and save those. You could always do more later if you realize you need them. Oh, I did it again. I can't start with a 4 for TV, so TV4. All right, so you may only have needed to create 2 of these. You may have also created a bunch like I did. I created all of these. At minimum, whatever you're viewing as your moderator, you would have needed to create high and low for that. So say we were viewing TV as our moderator, and we only wanted to go with the 4 versus 1 hours. All you would have needed to create right then is these first 2. With the ordinary version of education, because we want to check the slope of that to do our simple slopes test, just the significance test. This is all we would need. Then you would do the reverse if you wanted to check with the other as the moderator. Then we have the high and low for each, which will actually be more useful for graphing probably than for anything else, because the slope is given to us by the regression equation. And we only need to grab these specific high and low points to make a really good plot. So let me show you, if we want to test the simple question of using simple slopes, is there a difference in the relationship between education and happiness among those who watch 4 hours of TV versus those who watch 1 hour of TV? We can do that in the following way. Go to your linear regression. Just going to clear this out. We'll always be predicting happiness here. That doesn't change. But think about what we're actually using here. We're going to use our ordinary version of education, which is, oops, I grabbed the Z version. This one, just education, highest year of school completed. And then let's first check this at high levels of TV, which we're calling four hours of TV. And then the interaction that uses these 2, which is going to be TV4 times education. And let's see what that looks like. Okay, when we are looking at people who watch a large amount of TV on average, we see that, in fact, there is going to be a significant slope of education here. And in particular, it's 0.043. Because that's positive, that means for every year of school completed, happiness goes up by 0.043 points. Now we want to compare that to our other point, which is 1 hour of TV versus 4. So go to your linear regression. Get rid of anything that has anything to do with TV here. We can keep the same education. But then we want hours 1 TV and the corresponding interaction between the 2 that we have here. The hours of TV version of TV and the original version of education. I've ended up doing EDU versus EDUC, but we know that those are the same. You should probably be more consistent when you can, just so as not to get yourself confused, but we know in our limited set of variables, those are both education. Interesting. So here we see that we have, again, we still have a significant relationship or slope here, but it's about half as much. Instead of 0.043, it's 0.026. So we can see that the slope is different, which is to say that with people watching less TV, now with this one, the effect of education is not as steep. But is that difference between these 2 significant? Sometimes you'll find that one of these is significant and one of these is not. And by one of these, I mean when you run it with 1 hour of TV versus 4 hours of TV, the high versus the low version. In this case, they're both significant, but that doesn't mean that one can't be enough steeper than the other such that it has a significant difference. To test the significance between these, SPSS does not have a very easy built-in way. So what we want to do is take our numbers and copy them over to a t-test calculator. You can look for one online, or I will link a couple below. When you do this, what you want to do is find one that compares slopes I have one to show you, or really any t-test calculator that allows you to run the t-test from a mean and standard error, or in this case, slope and standard error, but the calculation would be the same. So if you enter where it asks for means, if you enter your slope or your b, it will work for the test we're about to run. Here we'll also want to take note of our descriptive statistics, which I told you to turn on earlier, and now you'll see why. Here we can see that we have 2,306 in our sample. We'll need that plus information from our two coefficients tables to do this calculation. Here I'm using something on danielsoper.com. He provides some really good calculators, and I can say that this one appears to be accurate. Other ones like this one from GraphPad, which says it's just a basic t-test calculator, will also work when you use the SEM and N setting. I like this one because it says we're actually doing the difference between two slopes. Really, it's the same thing, but you know it was built for this exact purpose. It doesn't matter which one you treat as sample 1 or sample 2, or test 1 or test 2. So 2306 was our sample size here, but what was that other information we needed? For this one, our slope is 0.026, and then we need the standard error of that coefficient, which is right next to it, 0.005. That may not be very accurate, so you can double click on this, then click on it again, double click on it again to get the more accurate number. You can do that for both of these or not. It depends on the accuracy that you need. I'm going to go for the accurate route and grab these at high accuracy. So I've put in here the N, slope, and standard error from one of our tests. In this case, it was the test that we ran second that I'm putting in here, but it doesn't matter. Then we want the same information from the first test. So this was the one with 1 hour of TV. Go back up to your first test and let's see. Our sample size was the same, but our coefficients are a little different. Slope goes here. Sample size is the same. And notice that I've grabbed these each time from the education, which is here, the first line, well, after the constant, because we're testing that slope under the two conditions of high and low TV watching. So now I've entered the high accuracy version of all of these. And there's already some results here from when I'd entered one earlier. Just ignore that. This should be blank if you just started the page. Click Calculate. And now we get our answer to the question of, is there a significant difference in the relationship between education and happiness for those who watch 1 hour of TV versus those who watch 4? The answer is not quite a significant difference, because our probability here is just above 0.05. So while there clearly is a noticeable difference to our eyes in the numbers, and if we were to graph this in the slope, it's not quite statistically significant. However, at 0.08, remember that that's about 92% confidence that there's a difference between those in the real world. So it is a pretty good result. You would report here this t-value and the probability statistic in order to tell us overall what this looked like. Now we can run this entire test again using the standard deviation versions. We'll complete the plus or minus 1 standard deviation version simply by swapping out the variables for the ones we've already created. Get rid of the one based on a specific number of hours. Instead, let's put in high then low TV. And again, always make sure you use the interaction that contains the two other variables. Then run the one that's low. If we no longer want to use 1 in 4 hours of TV, but instead use plus and minus 1 standard deviation of TV watching, we simply run it using those variables. It actually was already set up here, so you might notice I took those out. I was just testing it. So if it didn't match what you still had in there, that's okay. So we want to take either high or low TV and move it over, the Z version now. And of course, the interaction variable that matches with these two. Click OK. We now see a different slope than we had before of 0.033, and that this is significant. That's with high TV watching. What about low TV? Very interesting. We get our first very obvious result that we're likely to have a difference between slopes. Here, we see the slope has fallen to almost nothing. Instead of 0.033, it's now 0.007. And this is no longer significant. This alone is interesting in that the relationship between education and happiness is not significant among those watching lower amounts of TV. So, we definitely want to test the difference between these two slopes as well. What we'd want to do is again take our slope and standard error from each one, as well as the sample size, which won't change, and enter it into our calculator. I've already done this just to speed things up. So here we have these new results based on the plus or minus 1 standard deviation, where we have very little slope in one case and a pretty strong slope in the other. Let's see if this is enough to be significantly different. It is 0.003 p-value. So here we can say that the slope is different. Now, why is that exactly? We'd have to go back and look at our values, but it has to do with the fact that the two standard deviations apart these are, because plus 1 and minus 1 are 2 apart, since they're both 1 away from 0, is either more or less difference than the amount that we had when we used 1 and 4 as our hours of TV, as well as they may be at a different point along the scale, rather than when we just go up or down plus or minus 1. You would often find these results to be a little bit different in this case. The further you go down the scale in either direction, high or low, like very high and very low versus high and low, or a little high and a little low. So it's not shocking or concerning necessarily that we got this in this case and not the other. But this would tell us that in this case, our simple slopes analysis tells us there is in fact a difference in the slopes at those two set values of TV watching. So if we go back to here, we can remember how many ways we could run this because we've created all these variables, but you only need to run the ones that you care about. The next thing you would want to understand is just simply what it would mean if you swapped one of these out. So we used only regular education. If we swap that out for high or low education, it would be the effect of, say, in this case, low TV when, say, education is high. And you could test all of those. But normally, you will want what you're considering your predictor to be this one with the ordinary version, like education, and the one that you've thought of as your moderator split into the high-low and run twice for your simple slopes test. If to you both can be the moderator, then flip it, and you would run ordinary TV with the high and low versions, however you chose to define those, of the education variables. And that would give you the answers that you need. So now we'll move on to graphing. To create plots, we'll want to run regressions that are back to our basic version, where nothing is a high or low version or anything like that, but just the plain old variables. That, or we'd want to run it with just the z-score or centered variables, but not the high or low ones either, just the z-score versions. So here I've got just the original versions already entered. So this would be if you want to use set points rather than standard deviations. So if you wanted to use, say, what we did before with the certain number of hours of TV or certain number of years of education, you may need to display that in a table or plot for your work. So run this regression. And what we'll need to do is realize that everything contained in this coefficients table gives us the exact formula for our regression line. And in Excel, we can then transfer that information in order to give us an exact prediction for happiness for the precise levels of education and TV viewing. I've already got this set up to show you what this will look like. Copy over from here the constant, which comes from the first line, which is also your y-intercept. Then the coefficient for TV here, education here, and the interaction, which is here. I double-clicked into each of those to get the high-resolution version, and that gives us the formula. Our formula is basically the y-intercept plus whatever our TV value is times this coefficient, plus our education value times this coefficient, plus the combination of these two times another coefficient all added together. Here I have a column that simply calculates TV times education here. You'll need to recreate that, and you should go ahead and make 4 rows like I did here. You might need more depending on if you're doing something complex, but what I'm going to show you will require only these 4. So these are just labels. These I've entered right from here. This I just put predicted as a reminder that we're getting it from a formula. These 4 simply take the cell next to it times the next cell. Well, the cell 2 cells over and the cell next to it. And then this one is a little bit complicated. This takes whatever is in here and multiplies it times this times that, and the one here times that, and adds all of them together. You'll notice dollar signs in here. That keeps them fixed. So the references to this entire row, you'll want to do that. Instead of just A13, it's $A, $13. One neat way you can do that is after you selected the cell, you can press F4 and it will automatically lock it in for you by adding dollar signs. I do that so that I could just copy these down. What I did then was take this and copy it in this way. And now this one automatically refers to the top row rather than just a row above. And even at the bottom, it automatically understood that these are the reference cells that don't move because they have dollar signs, but that these were to move down to the same row. So again, it's the constant plus whatever we enter times TV plus whatever we enter times EDU plus whatever it calculates is the multiplication of these two times this number here, just all added together. And that will give us our prediction. This one that you see here is based on the real score, so that's also what we would enter here. So if you remember before that we might want to consider TV of 1 or 4, not quite sure why that one has all the zeros. Let's get rid of those. And education, we wanted to be set either at 12 or 16. By entering that, that gives us all of those combinations, and that would be all we need to then make our graph. I'll show you how to do that with one of these. But notice, this is now an incredibly powerful tool. Okay, we know we wanted to see what is our predicted happy when we watch 1 hour of TV and have a high school education, 4 hours of TV, high school education, 1 hour of TV, college. 4-hour college. But we can also toy with other numbers here. We could just put in, if we're predicted right now it's 2.17 happy, we could say, what if we watch 0 TV and have 20 years of education? That predicts a very high level of happiness on average. What if we watch 8 hours of TV a day but didn't go to high school? predicts a fairly low level of happiness. You can put in any ones that you want as reference points, and that can be incredibly powerful for providing the department with what they've asked you for, providing you with powerful statistics and answers to the questions you were seeking from the very beginning. If you're using the z-score version or a centered version, it's very similar but a little different. We want to generate the numbers here again. Well, it's really the same. The difference is that you'll be thinking in standard deviations again. You would want your z-scores for everything. And we're just doing this again to generate the numbers we need. And you would come in here and copy out all these numbers, mainly from here, that you need. I've done that already. Notice 2.17 is here, and so on. So this one's already done. And you would just copy this whole block. There's no new work to do here. These calculations are the same, so you just copy the whole thing. But what would we do there? Well, now we're thinking in standard deviations. We would do what we did before, like this. I mistyped this -1. There we go. And again, we get our prediction for each of those, which is going to be similar to what we were getting before with our testing. However, again, you can then type in your own to get whatever you'd like to know. What if it's a full 2 standard deviations below the mean on TV? And 2 above on education and 2 below on TV. What do we get? Oh, a very high happiness score, and so on. But putting these back to the basic thing you would almost certainly want to use. And if you remember, this is our version that was significant, so it'd be the best one to graph. I'm going to now show you how to graph this. We actually have to create an alternate data set in SPSS, but it's pretty easy. So let me show you what that looks like. You'll want to create 3 variables, call them TV, education, and happy. And here you just enter the pattern that we know we want to use, which again mimics what I've done here. You could copy and paste these over as well. We just want to represent every condition. -1, -1, 1, -1, -1, 1, and 1, 1. It's all the possibilities. And then take your predicted values from here and paste them right into SPSS. We can now create a plot. Go to Graphs, Chart Builder, Line, and then we want this multi-line with the colors. Put happy on your y-axis. Now here you could put either in either place, but the way we've been thinking of it mainly is that education is our predictor, so it would go here. And then the other one you put on set color, which I know isn't obvious, but what it means is it's going to make a separate line with a different color for each of these. Again, it would make just as much sense in my mind for this particular study to have TV down here, maybe even more, because you could more easily change your TV viewing habits, right? So you'll get something like this, and you might want to change it up a little because we can't see that change very easily, but we can see that when TV viewing is low, there's a much larger slope here than when TV is high, which is exactly what we expected. This is that tiny slope that's not significant, and this is that one that's a little larger and significant. You can clean this up to look better in a number of ways, mainly by changing. I just double-clicked to get into this editor and double-clicked over here to change the scale. Find the Scale tab. Try to zoom it in a little in this fashion. I would change the increment to a smaller one like 0.1, and I don't like having the margin up top, which means it shows more than your maximum. But that's up to you. I don't really like that much either. Let's see. 2.5 is actually what I meant to do. Oh, that looks better. You could toy with that to get what you like. But here we get a really good depiction of this interaction. You can think of it in a number of ways, but you could say If you have low TV viewing, then becoming more educated or being more educated is associated with higher happiness. If you're watching a lot of TV, your happiness is probably lower altogether. That's the main effect here, the distance between these just height-wise. And also, your level of education won't have much to do with it. So another way of saying this is you need to limit your TV time and have a high education to maximize your happiness. And at the lower ends of education, how much TV you're watching doesn't make as much difference, which is interesting. There are many other ways to interpret that as well. And again, we could flip this and make all sorts of changes to the editing of this to make it look nicer. But that's how you would graph this. If you wanted to do that from the other versions that we made, you would simply pull that data in and use those labels accordingly. Another thing you can also do is have 3 levels here by including the one that is neither high nor low, but the original versions that we used. So you could have low, normal, and high, low, normal, and high on one or both of these axes. All you would do for that is in this z-score area to add zeros where you want to use the middle or normal score rather than the high or low version. If you do that, you'll get something like this, which I've already filled in for you. And to show you what that looks like, let's go ahead and swap these to say, we'll look at our TV viewing at levels of education. We now get 3 lines with 3 points. You can hardly tell there's 3 points just because these are really straight linear trends through all 3 of these. But this starts to look really neat. And this would still be part of what you could call a simple slopes analysis, but at 3 points. If you want to test the significance between mid and low and mid and high, you'd have to go back and run the testing that we did with mid and high rather than low and high as we did to compare those differences. But these are really compelling ways to do this. Don't forget to also change this so that this looks a little better, but if you wanted to use the scores, here we could have something like 1 hour of TV, 3 hours of TV, 5 hours of TV. And over here you could say no high school, college, or high school, college, and graduate school, though you'd have to pick some number to represent graduate school, like 16 or 18 total years or something like that. But just look at how compelling that could be. And we can see here in this case, the slope just keeps changing as you go from one group to the next here. The highly educated, TV doesn't matter. The moderately educated, TV is associated with a decrease, although maybe not significant, in happiness. And among those with low education, we see here that TV is related to lower happiness as you watch more TV. And so this is a way that you would do this and show the results. I hope you really enjoyed this. Again, I have a linear regression class you can check out, or I'm available as a consultant if things have gotten trickier than this, or if you don't want to do the work. You can see those links below. Please like and subscribe, and thank you.